Hi everyone. I got a question today on 25.12 and the student had indicated that the question was not up on the YouTube and on YouTube. So yeah, so that reminded me, I was waiting for people to ask if they wanted another YouTube walkthrough on some of these problems. So here I go. I'm going to take a look at 25.12. I typed out the question here. Consider a population in which the frequency of allele A is 0.7 and the frequency of allele little a is 0.3 and the alleles are codominant. What will the frequencies be after one generation if the following occurs? And then this question is divided into 4 parts, but we are just going to take a look at the first part because they are all the same. Once you can do the first part, you can do the others as well. So we are looking at different fitness levels, and we are going to use this little W here, which I think population geneticists refer to that as omega, so the lowercase omega symbol, Greek symbol. So the fitness level of a homozygous big A genotype, we're going to say that's 1.0. For the heterozygote, we are going to say the fitness level is 0.9. And for the homozygous recessive, or they're codominant, so the homozygous little a is going to be 0.8. So it doesn't really matter too much if they're codominant or dominant or whatever. It doesn't really matter. We just want to know what the frequencies are going to be once these guys reproduce. So we have to assume that they are originally in equilibrium, and now some change has happened, maybe climate change or whatever, and now we have different fitness levels for these different genotypes. First thing we need to do is estimate the genotype frequencies in the current population. Okay, so how are we going to do that? We are going to use our formula here, p squared plus 2pq plus q squared equals 1, and we know q equals 0.3 and p equals 0.7 in this current generation. So let's estimate the genotype frequencies here. This is going to be the genotype frequency of 2 little a's here, the 2 little a genotype. This is the homozygous big A genotype, and these are the heterozygotes. So q squared is going to be 0.3 squared, p squared is going to be 0.7 squared, and this one right here is going to be 2 times 0.7 times 0.3, right? Where are these numbers coming from? They're just coming from right here. They're coming from the question. The frequency of the p of the big A allele is p is equal to 0.7, and it's 0.3 for q. Okay, so now we have our genotype frequencies for homozygous big A, heterozygous, and homozygous little a. Okay, so we can just do the math here. This is going to be 0.49, this is going to be 0.42, and this is going to be 0.09. So 9% of the population is homozygous little a, 42% is heterozygous, 49% is homozygous big A. Now, if you look at the back of the book, we have some complicated formulas we can use to figure this out. And I don't think if you can memorize the formula, I don't think you get really much of an understanding of what's going on here. So I like to do this in the following manner. So just assume these numbers right here are the percentage of each genotype that actually contribute gametes to the next generation, or alleles to the next generation. So that means out of the AA genotypes, because the fitness level, the omega level, is 1.0, all of them are going to contribute to the next generation, are going to donate alleles to the next generation. For the heterozygotes, only 90%, 0.9, are actually going to contribute gametes to the next generation. For these homozygous recessive A's, only 0.8 will actually contribute gametes to the next generation. So, or alleles to the next generation. You can say it however you want. These are the ratios of these genotypes that are actually contributing to the gene pool of the next generation. So let us assume a random, we grab 1,000 individuals from the current population where 49% are homozygous big A, 9% are homozygous little a, and 42% are heterozygous. So 490 are going to be homozygous big A, right? 49% of 1,000 is 490. 420 are going to be heterozygous, and 90 are going to be homozygous recessive. Now we know from these fitness levels, someone already calculated these fitness levels for us, whatever event happened, you know, climate change or something, we know these homozygous little a's are less likely to reproduce and contribute to the gene pool. So we're going to multiply this by 0.8 because that's the fitness level, and I'm going to take out my calculator here. 90 times 0.8 is 72. So only 72 of these 90 are going to contribute to the gene pool. For the next one, these 420 heterozygotes, only 90% of them, 0.9, are going to contribute. So 420 times 0.9 equals 378. And all of these, all 490, because this is times 1.0, right? All 490 of these are going to contribute to the gene pool. So let me clean this up a little bit. So after these calculations, after considering the fitness levels, out of 490 homozygous big A genotypes, 490 will contribute to the gene pool of the next generation. 420 of the heterozygotes, of those, only 378 will contribute to the gene pool. Of 90 homozygous recessives, I keep saying recessive, sorry, these are codominant, but again, it doesn't matter for this question. Of the 90 homozygous little a's, only 72 will contribute alleles to the next generation. So we would add these up. Quickly, I could probably do this by hand, but I'll use my calculator. Okay, so we have 870 alleles total being transmitted to the next generation from these progeny because of the fitness effects. So if we want to know the frequency of, let's say, little a in the next generation, we just add well, let me step back a bit. How many big A alleles are these 490 individuals contributing to the next generation? They have two. Each one of them has two big A alleles. So we're just going to multiply this by 2, and we're going to get 980 total, right? 490 times 2 is 980. Now, how many big A alleles are going to be contributed by these 378? Just 378, because they're heterozygous. They're also going to contribute 378 little a's, right? For these 72, how many little a's are they going to contribute to the gene pool of the next generation? Well, they each have 2 little a alleles, so it's going to be 144 little a's. Now let's add this up here, these numbers. So 980 plus 378 plus 378 plus 144 equals 1,880 alleles in the gene pool of the next generation. Okay, now we can calculate the frequency of little a. So we have to add this one right here, 378 little a's from the heterozygotes, 144 little a's from the homozygote little a's. So 378 plus 144 divided by the total number of alleles. Let's see what that adds up to. So 378 plus 144 is 522 divided by 1880 equals 0.278. So this is the frequency of, this is Q, this is the frequency of little a in the next generation. Remember, it was 0.3, and because of these fitness effects, because of the decreased fitness of the heterozygote and the homozygous little a relative to the homozygous big A genotype, the allele frequencies are changing from generation to generation. Q, little a is going down, and P, or big A, is going up. And how do we get P? P is 1 minus Q, so 1 minus 0.278 is going to equal 0.722, I believe, 0.722. Okay, so I think, and that is the answer to, yep, okay, check the answer at the back of the book, and this is the correct answer. So these are the frequencies of, or the values of Q and P in the next generation. Okay, so now that you know how to do the problem, you can just do the same thing for B, C, and D, and check your answers at the back of the book. And I think you are finished with this problem, or we are finished with this problem. Okay, come and see me and ask questions for during the review session, or email me if you need additional clarification. Okay.